Okay, so my paper contributes to propositional dynamic logic. And in order to motivate propositional dynamic logic, let's recall transition systems, which are basically, well, structures that pop up all over computer science. So we have a set of states, a set of transitions or arrows between the states, which may be labeled by transition labels. And then perhaps we can have also state labels labeling states, right? Given specific transition systems or sets of transition systems, we may ask a number of interesting questions. Like, for example, if there is a transition connecting specific states or states having specific labels, or more generally, if there is a transition induced by some specific sequence of labels that connect specific states, then we can ask if specific sequence of transition labels induces transitions that always lead from states satisfying some precondition to states satisfying some postcondition, right? So these are two broad kinds of questions we may be asking about transition systems, which, as I said, pop up everywhere in computer science, for example, in automata theory, in semantics of programming languages, in planning, and so on and so on. Okay, so what is propositional dynamic logic? Propositional dynamic logic is a modal logic which offers a specification language that is able to express many interesting properties of transition systems. So, as I said, propositional dynamic logic is a modal logic, which means that its language contains modal operators, boxes, which in this case are indexed by so-called programs. And the formulas of the form box alpha phi, where phi is a formula, are in general read as phi holds after each terminating execution of program alpha, or more generally, phi holds after each successful execution of action alpha. What is typical of PDL is that programs or actions are structured. Right? So in addition to propositional connectives, we have operators on programs. And in case of PDL, we have operators that express consecutive execution of programs. We have a choice operator, we have a finite iteration operator, and then we have a test operator, which turns formulas into actions. Programs are semantically interpreted as binary relations, where atomic programs, the relations given by atomic programs are well, components of the underlying transition system. And then the relations for complex programs are computed out of simpler relations by applying well-known operations on binary relations like relational composition, union, reflexive transitive closure, and so on. So PDL can express many interesting properties of transition systems. For example, it can express partial correctness, meaning statements of the form that if you execute alpha in a state satisfying phi and alpha terminates, then you are guaranteed to get to a state where psi is satisfied. And importantly, the program connectives of PDL allow you to represent standard programming constructs as if, then, else, or while loops. Okay, so this is classical PDL. My work is in many-valued PDL. And what's the motivation for going many-valued? Well, basically, in many application scenarios or situations, we need to express more than standard transition systems allow us to express. Like, for example, many times interesting features of states are specified using vague or graded notions. Okay? Or often we need to look at state transitions associated with actions as being weighted or having a cost. So it's not sufficient to know that some state T is reachable from state S, but we need to articulate the cost of reaching the state T from state S by some specific action. So all this translates into so-called weighted transition systems, where everything is as before, with the only exception that we select a set of weights, W, and the labeling functions, so the transition labeling function and the state labeling function, doesn't work with the two-element Boolean algebra, but it works with W instead, right? So for example, instead of saying which state label, for any specific state label that it applies to given state or not, we say to which degree the label applies to the given state. And similarly for arrows between states. Okay, so here's an example. And similarly as with transition systems, there are specific interesting questions we may ask concerning weighted transition systems. So for example, we can ask if it's possible to get from a specific state to another specific state by a transition that that has a weight above some threshold, or conversely, that we can get from a specific state to another state by a transition that which cost doesn't exceed some given threshold, right? Or we can ask if two given courses of action or sequences of transition labels, well, how do given sequences of transition labels compare when it comes to attaining some specific goal, right? As one special case of these questions, we can ask about shortest paths from a given node to from a given state to states satisfying some features. Okay, now let's be more specific about these sets of weights. So there are some natural assumptions we can take on board. For example, we may assume that our set of weights is linearly ordered, and we may assume that it actually has an algebraic structure, so it has some operations on it. For example, an important operation could be an operation of weight combination. There's also a close connection between weights and truth degrees of statements. Then, for example, if we choose some linearly ordered set, for example, a subset of the real unit interval, 0, 1, then it makes sense to include the extreme points 1 and 0 in our weight algebra. And these could represent absolute weight for 1 and no weight or 0 truth for 0. And then with each weight or with each weight or truth degree x, we may associate the converse weight or the cost 1 minus x. So of course, there are many ways how to instantiate this general template. And in my paper, I'm working with a specific kind of finite weight algebras, so-called finite Lukashevich chains, which are specific subsets of the 0, 1 interval. I won't give you the definition. You can look at the poster or at into my paper for details. In my language, programs are defined as before, and formulas are built up using propositional connectives, the module operator, and importantly, I'm using constants for elements of the weight algebra. My models are weighted transition systems where the weight algebra, of course, is the given Lukashevich chain, and then values for transitions corresponding to complex programs and values of complex formulas in states are computed using finite Lukashevich generalizations of the standard clauses or standard definitions. Again, you can see the details in the paper. Good. So what can we express in this framework? We can express, for example, we can express minimal costs of reaching certain states via certain actions, right? So what this means is that for each So for each formula phi and the program alpha, we have a formula in the language such that the value of the formula in a state S is precisely the minimal cost of accessing a phi state via some alpha action. So we may call this also the cost of the optimal path along alpha steps that reaches a phi state. So phi itself can be graded. So for example, such a formula gives you an answer if your goal is to get to a good restaurant quickly from the given state. So this formula
should come to an end soon or quickly.
Yes. I will. I think I will take 1 or 1.5 minutes from the Q&A time. So yes, I'm approaching the end. Okay, so we can express these optimal paths or minimal costs of accessing phi states via alpha actions by formulas. We can express comparisons of these minimal costs with respect to some given threshold. We can express comparisons between the minimal costs of attaining phi 1 via alpha 1 and phi 2 via alpha 2. So as a special case, we can compare some alpha 1 and alpha 2 as means of getting to some goals, to some goal specified by a formula, and so on. Okay, so in the final 1.5 minutes of my presentation, or the final 2 minutes, I will just state the main technical results on these finite Lukasiewicz versions of PDL. So the first result is that each PDL for all n above 2, PDL n is recursively axiomatizable. And this result is obtained by using a canonical model construction that is based on earlier work on many-valued model logics and a generalization of the filtration argument used in the two-valued case. Filtration gives us decidability because, well, it gives us a bounded finite model property, which shows that each PDL n is decidable. And then we also have a complexity result showing that exactly as two-valued PDL, each n-valued PDL is X-time complete. So the upper bound is obtained by a generalization of Brett's algorithm, and the lower bound is obtained by constructing an embedding of two-valued PDL into each n-valued PDL. Okay, so what I hope to have achieved in this paper, or shown in this paper, is that versions of PDL based on Lukasiewicz logic, finite value Lukasiewicz logic, offer expressive specification languages for weighted transition systems, and that the logics are technically well behaved, similarly as PDL. In future work, I would like to look at richer weight algebras, for example, infinite Lukasiewicz algebra or the product algebra. I would like to investigate the relation of this to the semantics of probabilistic programs and actions. And I would like to look at formalizing plans with graded deontic constraints. And that's it. Thank you very much.